Today we are going to see the fluctuations in grand canonical ensemble. As you know, in a grand canonical ensemble, the variables n, which is number of particles, and E, which is energy of the system. Actually, these two parameters are not fixed in a grand canonical. You have learnt it earlier. Okay. Since n and E of the system are not fixed, so it is obvious that there will be a fluctuation in measuring the values of n and E. So you can say in case of grand canonical ensemble, two fluctuations take place. First one is fluctuation in energy E, and the another is the fluctuation in the number density, or you can say the number of particles, or simply density or concentration. When you say concentration, that means number of particle per unit volume. Okay. So when you will calculate the fluctuation in the value of n, that will also mean we are just calculating the fluctuation in density or concentration, that is number of particles per unit volume of the system. Actually, the fluctuation of energy in grand canonical ensemble, that can be calculated on the same line as you have calculated the energy fluctuation in case of canonical ensemble. So I am not going here to calculate the energy fluctuation in grand canonical ensemble. I am leaving it just a homework for you. You watch the video on calculation of fluctuation in energy in case of canonical ensemble, and on the same line you have to try to find the fluctuation of energy in case of grand canonical ensemble. So here our aim is only to discuss the fluctuation in number of particle n, or you can say the fluctuation in density or concentration rho, which is number of particle per unit volume. Okay. So definitely you should try yourself to find the energy fluctuation in grand canonical ensemble, as I have told you, on the same basis as I have calculated this fluctuation in case of canonical ensemble. Okay. Only the partition function will be changed, all things will remain same. So now let us try to find the density fluctuation in case of grand canonical ensemble. In fact, in case of grand canonical ensemble, if you want to find the average number or mean number of particles, how you can define it? We have learned learned for finding average value of any parameter earlier. So on the basis of that concept, you can say that the average or mean value of number of particles, which I have denoted here by n inside the angular bracket, that will be simply defined like this. This is summation over capital N, summation over small n, n times exponential of beta times mu n minus e n n, and divided by this double summation exponential of beta times mu n minus e n n. Okay, you know it. Here you know this beta is the parameter defined by reciprocal of this statistical temperature. It means beta has been written at the place of 1 by tau, or you can say 1 by kT, where k is Boltzmann constant, you know. Now we will simply differentiate partially this average value of number of particle with respect to the chemical potential per particle mu, keeping this energy E and N constant. Okay. So let us see, when you will differentiate this equation 1 with respect to mu, keeping the energy value E and N constant, what will be your result? Actually, I have not done here all the steps of differentiation. This is just a simple differentiation and you can try it. I have directly written the result that the partial derivative of average value of n with respect to mu when v and t are constant, that will be equal to, when you will do this differentiation, you will get the result like this. This is beta times summation over capital N summation over small n square exponential of beta mu n minus e n n over summation over n summation over small n exponential beta times mu n minus e n n, and minus summation over n summation over small n times exponential beta times mu n minus e n n over summation over n summation over small n exponential beta times mu n minus e n n whole square. Okay. Now see this first term inside this square bracket. What is this? Can you recognize it? This is simply the average value of n square. Okay, average value of n square, and the quantity inside this curly bracket. What is this? You can recognize it. This is the average value of n. Okay, so this will be simply beta, and at the place of this first term we will write average value of n square minus, at the place of second term we will write a square of average value of n. Okay, so del n by del mu at constant v and t, this is equal to beta times average value of n square minus average of n square. Okay, and this quantity, that is average value of n square minus average n square, that has been written like this. This is average value of delta n square. Okay, you know, this is actually called the mean square fluctuation in n. Okay, this is mean square fluctuation. Okay, so the partial derivative of n with respect to mu at constant v and t, this is just equal to beta times average value of what? Average value of delta n square. Okay, which actually represents the mean square value of the quantity n. Okay, now you can easily define what will be the relative mean square fluctuation. You know, for getting the value of relative mean square fluctuation, we simply divide the mean square fluctuation by the square of the mean of that quantity. So this, if your aim is to find the mean square relative mean square fluctuation of density rho, that will be defined like this. This is average value of delta rho square divided by mean value of rho square. Okay, and at the place of this delta rho square we can write this is mean of rho square minus mean of rho whole square and divided by mean of rho square. Okay, but as you know, this rho is equal to what? This is n over v. So if at the place of each row we will substitute n over v, then in numerator and in denominator this v will cancel out. Okay, and so at the place of rho you can simply write n. Okay, so this will be simply equal to delta average value of delta n square over mean of n square. Okay, I think we have understand. Rho can be replaced by n because this v will cancel out. Okay, now let us see this equation 2. In this equation 2 you can see that this partial derivative of average value of n with respect to mu, that is equal to beta times this much. Okay, And so from this equation 2, we can write that this partial derivative is equal to this much. I have just repeated it. And beta is equal to 1 over kt. So at the place of beta, I have written here 1 over kt. And so from here you can see that the mean value of delta n square, that will be equal to kt times this partial derivative of n with respect to mu at constant v and t. Okay. Now in this equation 3, we will use this value of average value of delta n square. At the place of this delta n square, we will substitute it. So you can write that this mean value of delta rho square over mean value of rho whole square, that is equal to mean value of delta n square over square of mean value of n. And that will be equal to what? You can see this is equal to this much. Okay. So at the place of this mean value of delta n square, we will write the expression which we have obtained in this equation number 4. Okay. But here delta, the mean value of this n has been simply replaced by n. Why? As you have learned earlier, if the number n is very large, then approximately n is equal to its mean value. So at the place of this mean value of n, we can write simply n. Okay. So I have written here kt over n square. At the place of this mean value of n square, I have written only n square. And at the same time, at the place of this mean value of n, I have written here only n. So this is simply kt over n square, partial derivative of del n by del mu at constant v and t. Okay. Now we will see what will be actually the value of this del n by del mu at constant v and t. And for this you have to think which you have learnt earlier. While dealing with the classical ensemble, particularly for Maxwell-Boltzmann gas, you have seen that the number of particles, which is almost equal to average value of this number of particles, you have learnt earlier that this is simply equal to e to the power mu by kt times 2 pi m kt over h square whole to the power 3 by 2 times v. And from here you can see, you can get the value of this partial derivative, that is del n by del mu. Actually at the place of this mean value of n, again I have written n only. As you can see in the RHS of this result, when we will differentiate partially with respect to mu, keeping this v and t constant, only mu is variable and all other factors are constant. So the derivative will be what? This will be 1 over kt times e to the power mu by kt times this much. This is 2 pi m kt over h square whole to the power 3 by 2 times v. But let us see this factor which I am writing inside this bracket. What is this? You can see this is simply n. This is n. So this is equal to n over kt. So the partial derivative of n with respect to mu when v and t are constant, that is equal to n over kt. Now we will substitute this value of this partial derivative of n with respect to mu which we have obtained in this equation 6 in this equation number 5. But as you can see, this term or this term, this is actually what? This is actually the relative mean square fluctuation of rho or mean square fluctuation of n. And that mean square fluctuation is simply written by the symbol delta rho square. Okay, That is written as delta rho square, as you have learnt in the lecture on fluctuation earlier. So this delta n rho square or delta n square, that will be equal to what? That will be kt over n square times n over kt. See here, this is kt over n square, and the value of this partial derivative we have obtained, this is n over kt. So here this n and this square will cancel out, this kt will cancel out, and our result is simply 1 over n. Okay, this is the relative mean square fluctuation. Now if your aim is to find the relative root mean square fluctuation, what you will do? You will simply take the square root. So the relative root mean square fluctuation in this density will be equal to what? That will be equal to 1 over root n. You can see this result is same as that was obtained in case of the energy fluctuation in case of canonical ensemble. So the relative root mean square fluctuation solely depends on the number of particles. Okay, number of particles. But as you know, particularly in case of the statistical system, the number of particles is very large. So if you consider that the number of particles n is very large, it is almost of the order of 10 to the power 23, then actually this value n to the power minus half, that is 1 over root n, that will be actually equal to very small, or you can say that will be almost negligible. Okay, and so you can say that this relative root mean square fluctuation, this will be negligibly small when we are talking about the grand canonical ensemble consisting of a large number of particles. So in this condition we can say that the number of particles remains almost constant, and so the grand canonical ensemble will behave just like a canonical ensemble in this condition. And as you have learnt earlier, that at the place of Helmholtz free energy function, this is f. This f is what? You know, this is Helmholtz free energy function. And this omega, this is grand potential. You have learnt earlier that at the place of Helmholtz free energy function, in case of grand canonical ensemble, we use the grand potential. It means the role which is played by the free energy function in case of canonical ensemble, the same role is played by the grand potential in case of grand canonical ensemble. But when you consider that n is very large, then in that condition there will be no difference between the grand canonical potential and the Gibbs free energy. It means omega plus mu n will be almost equal to f, and that's why we simply say that in this condition the grand canonical distribution becomes identical to the canonical distribution. Okay. However, there are some exceptions like phase transitions or critical region, which you will learn in the lectures in my lectures on phase transition, that in case of phase transition or particularly in critical region in phase transition, the fluctuations becomes very large. Okay, and so in such cases the formalism of the grand canonical ensemble will provide a correct picture of the physical situation and will be preferred. It means if you are dealing with the problem of phase transition, then you have to consider the formalism of grand canonical ensemble, not the formalism of canonical ensemble. Why? Because in that condition you cannot neglect the fluctuation of this density or this number of particle. You have to take it under account, because in that case fluctuation in number of particle is very large and we cannot neglect it. And this is the reason that while dealing with the problem of phase transition, the consideration of the grand canonical formalism is more superior or more accurate. We cannot consider the system as a canonical ensemble in that case. So I think we have definitely understand clearly how we can find the fluctuation in density or concentration or number of particle in case of grand canonical ensemble. This was a just simple problem, and as I have told you, you have uh, himself to calculate the energy fluctuation in this case on the basis of the calculation which I have done in case of canonical ensemble. So thank you very much.